Mountains, rocks, and desert as far as the eye can see. An alien world. Rugged, barren, lonely. But something big is in the making here. Gigantic antenna dishes are moving into the mountains. On an extraordinary mission for man and machine, in a place that's extreme in every way. On one of the highest plateaus in the Atacama Desert lies the largest observatory on Earth, ALMA, the Atacama Large Millimeter Array. Powerful telescopes peer into the nebulae in space.
This absolutely fantastic. It's at least 10 times better than anything we had before.
66 massive antennas observe the birth and death of stars and planets.
ALMA is going to be able to look at planet formation in action.
ALMA is giving us this incredible sensitivity, this incredible level of detail to a part of the universe that we really don't know that much about.
It's the world's most advanced telescope, exploring the origins of our universe. The Atacama Desert in northern Chile is a remote, inhospitable place. It seems otherworldly, like a distant planet from a science fiction movie. The arid plateau and rugged volcanoes are part of the Andes, whose peaks rake the skies at over 19,000 feet. In the midst of this forlorn landscape, nearly 10,000 feet above sea level, lies the base station of the world's largest observatory, ALMA, the Atacama Large Millimeter Submillimeter Array. But the heart of the installation is actually 17 miles away and much higher up. At 16,400 feet, the Chenantour Plateau is as high as the base station for climbers on Mount Everest. This is the site of ALMA's 66 radio antennas. The vast installation has a long and fascinating history. The project began with a conversation between scientists on 4 different continents, according to John Stoke of the U.S. National Radio Astronomy Observatory.
The history of the ALMA project goes back actually many decades, and in each of the regions of the world that are now contributing to ALMA, there were ideas about building an array of telescopes. It was more recently that all of those partners got together and decided to build one really big telescope as opposed to each partner building their own.
ALMA is the remarkable product of a 20-year global effort to build Earth's most advanced observatory. The installation is a partnership of Europe, North America, and East Asia in cooperation with Chile. The Operation Support Facility, or OSF, is the base station and control center of ALMA. From here, the antennas on the high plateau are monitored and controlled. A challenge for scientists around the world. This is pioneering work. ALMA is opening a new window to the universe. The antenna dishes don't receive visible light, but radio waves. In a sense, they're listening to the stars. The base station of the antenna array lies in the middle of nowhere. The approach roads stretch for hundreds of miles across the desert. Antennas are brought here from Europe, North America, and Japan. Over 40 feet in diameter, The ALMA's dishes are so big, they can't be transported in one piece. They must be assembled at the base station. It's a labor-intensive process that takes several weeks to prepare a single antenna ready for use. Three separate areas are set up for the various assembly stages of the antennas. Teams from Europe, Japan, and the United States work in the open and in an enormous hangar. The antennas are individually designed, but they all have to meet the same demands. They must be precisely synchronized in order to scan the heavens as a single telescope. Astronomers have high hopes for ALMA. The unprecedented accuracy in long-wave radio observations is expected to help answer many important questions. How are solar systems formed, especially ones like our own, stars with many planets rotating around them? And are there rocky planets similar to the Earth that rotate around their central star at just the right distance to have water and support life? The search for planets similar to our Earth has intrigued human imagination for centuries. With ALMA, astronomers hope to understand how planets are born. This is Aaron Bowley's area of expertise. The astrophysicist from the University of Florida and his team were among the first to accomplish observations, even before ALMA was fully completed.
The way we think planets form is that dust first collects and eventually sticks together. And those then stick together to more dust, and eventually you have rocks. And then those rocks go to very large objects. And those rocks we see as leftovers today. We call them planetesimals. And when we look out and see them today, we call them comets and asteroids. And those eventually come together and they form very larger objects. And some of those are eventually going to become planets.
But how are planets actually born? For the first time, ALMA allows scientists far more accurate insights, previously hidden from the view of earlier telescopes.
We had the unique opportunity to use ALMA to look at planet formation. And we looked at the nearby star, Fomalhaut, in order to test planet formation theory. The reason why we want to look at Fomalhaut is because it's a very bright star. It's about 15 to 20 times as bright as the Sun. And it's actually fairly nearby. It's 25 light years away, which is really a stone throw in astronomical measurements.
Other telescopes have already discovered a broad band of dust around the Fomalhaut star. But in the long wavelength area of the ALMA surveys, astronomers have detected a sharply defined ring. Aaron's calculations and simulations produce startling results.
One of the best explanations for the Fomalhaut ring is that the dust is being shaped by two low-mass planets. And the reason we think that is that the grains are truncated sharply on both the inner and the outer edges. And we think the best way to confine that is to have two planets.
ALMA's unique sensitivity has actually begun to overturn many of the accepted ideas about the creation of planets themselves. In 2014, David Wilner of the Smithsonian Astrophysical Observatory pointed the ALMA array at a young star, 450 light-years away, called HL Tauri, or HL Tau.
When ALMA put this incredible resolving power onto HL Tau, what we saw really was shocking. It is a series of concentric rings of gas, beautiful rings. These rings had been predicted at some level by theories of planet formation, where a little planetary embryo grows large enough to start sweeping up the gas and dust in its orbit and clearing out a dark lane. But in HL Tauri, we could see at least 7 or 8 of these dark lanes all at once.
What was shocking about this discovery is that it's not supposed to be there. The star HL Tauri is less than 1 million years old, less than 1% of the age of our sun. Yet the ALMA telescope revealed that planets are forming billions of years earlier than anyone expected. Wilner's discovery with ALMA is already having an impact on our basic understanding of the universe and astronomy itself.
We didn't expect there to be an organized system of planet formation going on at this very early time. So ALMA is giving us this incredible sensitivity, this incredible level of detail to a part of the universe that we really don't know that much about. And so I'm sure that we will learn the answers to questions that we haven't even thought of.
With ALMA, astronomers will discover more about the origins of our own solar system and the Earth itself.
ALMA is not just a powerful telescope for looking at the end stages of planet formation through the debris, the leftovers, but for capturing the chemistry and what's happening during the throes of planet formation. Because that's going to give us some idea of what the building blocks are made of for planets. And that will give us some idea of what can go into terrestrial planets and eventually, perhaps, habitable planets.
It is the question of the ages. Are we alone in the universe? Or might other planets harbor life as we know it? For centuries, astronomers have looked to the stars in order to solve the mysteries of life. Now, the stars are beginning to answer. Using new technology, scientists have already discovered thousands of new planets beyond our solar system. And today, many telescopes are devoted to the search for a second Earth. Most observatories around the globe investigate the realm of visible light. Their eyes are lenses and mirrors, and these optical telescopes make it possible to observe space in the same light spectrum as is visible to the human eye. ALMA, on the other hand, consists of dozens of antenna dishes that record long-wave radiation. While radio waves are invisible to humans, ALMA can receive them both day and night. But a radio dish that could give us an image as sharp as a space telescope would have to be well over 6 miles in diameter. To construct a telescope of this magnitude would be impossible. But there is a solution. A number of antennas linked to each other to make them function like a single huge telescope. That is the ALMA concept. Positioned around an area with a circumference of about 10 miles, 66 antennas receive radio signals from outer space. The unimaginable quantity of data collected is fed into ALMA's supercomputer. It can perform 16 quadrillion, that is 16 million billion computations per second. It is this powerful computing ability and the complex programs developed during years of preparation that enable the antenna's signals to be converted into useful images. Even during the setup phase, astronomers were already carrying out the first optical tests. They explored the antenna galaxies, a spectacular heavenly phenomenon in which two galaxies collide. The clearest image so far was made by the Hubble Space Telescope. But what actually happens in those dark clouds around the collision area remained hidden from optical telescopes. Observations with ALMA have now revealed formerly invisible activity zones. This is where new stars are formed from gigantic clouds of dust and gas. very first test runs brought new discoveries. Normally, the millimeter and submillimeter wavelengths observed by ALMA cannot be received on Earth. They're absorbed almost entirely by vapor in our atmosphere. But the air in the Atacama Desert is so dry that it allows the radio waves to penetrate. One of ALMA's partners is the European Southern Observatory near Munich, Germany. This is where Carlos de Broek researches the most distant objects in space.
I look at the youngest galaxies in the beginning of the universe, when the universe was still very young, and so they're very distant. So they're about less than 10% of their current age. And I want to see how they were formed and how did they evolve into the galaxies that we see now.
Gazing into the depths of outer space is also a voyage into the past. It takes us back to the time some 13.75 billion years ago, just after the Big Bang, in which our universe was created. At first, there was only hydrogen and helium, the lightest elements. From these gaseous clouds, the first generations of stars were formed.
What we really want to know is when did these objects form in the age of the universe, and how did they form within the galaxy? Did they form in the center? Did they form outside? How did they evolve? And how did the heavy elements that we observe in the local universe, like carbon, nitrogen, and oxygen, how did they form from the hydrogen and helium that was formed in the Big Bang?
Astronomers can also detect these elements far off in the universe because ALMA allows atoms and molecules to be identified by means of their characteristic radiation. The heavier elements form in the hot interior of the star. Massive explosions send them shooting into space. Huge gas and dust clouds result, the raw material from which a new generation of stars develops. To peer into the cosmic dawn of new star formation, ALMA's antenna dishes must be precisely aligned. It's a painstaking process. Technicians use laser instruments to assure that each component is in the correct position. The 120 aluminum panels are placed with meticulous care. It takes 5 days for all the panels to be installed. Then the surface is complete. Before the finished antennas are delivered to the ALMA project, they're checked to make sure they work perfectly. From minute adjustments to broad sweeping turns. Then, further tests are carried out by the ALMA engineers. The person responsible here is the Deputy System Integration Manager, Bernard Lopez.
This here is the integration area. Here we receive the antennas from the vendors. Once we verify that they're accurate enough, we integrate the scientific instrumentation into them. After that, we verify that everything is okay, and only after that we deliver the antennas to the ALMA array.
First, the antennas are tested and calibrated. Using a transmission mast, a profile is made of each individual dish. The data is then turned over to the technicians in charge.
If you look at the antennas, you can see that it's built by a lot of panels, and each panel has several holes where you can find screws and adjusters inside. These adjusters allow us to mechanically set and improve the position of these panels and their form, the deformation of them. So from the holography measurements, we obtain correction maps. These correction maps are then handed over to our mechanics, and they work on the dish to set it and to improve it. And it's not necessarily enough to do it once. We have to iterate a few times over that until we really reach the point of accuracy that we need.
Each antenna dish has hundreds of screws. Every one must be adjusted by hand, mostly by only a few thousandths of a millimeter. The required precision of the surface is 25 thousandths of a millimeter, less than the width of a strand of hair. Only when everything is 100% perfect will the antennas be integrated into the ALMA array. It is the only way to guarantee that the dishes can work together with the necessary precision, despite being produced by different manufacturers. All antennas must move with the same timing. On command, they must pivot together to point at a target in the sky, and do it within a second and a half of one another. Only then can we witness the birth of stars. Now, these eyes on the universe are about to reveal shocking new discoveries about black holes and even life on other planets. At the ALMA telescope station in Chile, work never stops. Night and day, the giant antennas whirl in unison as they search the heavens. These massive dishes are designed to operate collectively and serve as one enormous eye, peering out at our universe. To achieve this effect, each dish must be able to make precision-timed movements on demand. The entire undertaking is an enormous challenge. In the control room, scientists work around the clock to keep ALMA on track. The astronomers here at the base station coordinate observation requests from colleagues from around the world. The astronomical observations are partly headed up by Alison Peck. Her specialty? Applying ALMA's power to the mystery of black holes.
Sounds very exotic when we say black hole. What we mean is when you have a large amount of mass in the center of a galaxy that collapses under gravity, it collapses and collapses, it just gets smaller and smaller and smaller until it occupies virtually no space. It has almost no volume. And so although it has this huge amount of mass, it occupies a very small space, but its effects can be felt at large distances because it has a very strong gravitational field.
An invisible monster star that swallows everything that comes near it. How can you observe something like that?
So nothing gets out of the black hole, even light. So the only way we can study black holes is by studying the gas that's near them. And this gas very often is being sucked into the center of the black hole. So it's falling in, but it doesn't fall directly in. It falls in like water going down a drain. It spirals around because it has angular momentum and it has viscosity. So that means that as it falls in from the outside of the galaxy, it spins around, and as it goes in, it gets hotter, it gets more energetic, and it radiates huge amounts of energy.
The enormous amount of energy released around a black hole appears as a bright, glaring light that surrounds the invisible center.
A lot of material that's falling toward the black hole does escape. One of the reasons for that is because you have strong magnetic fields with this material being drawn in. And this can cause matter to be shot in two directions in what we call jets, bipolar jets, away from the black hole.
Using ALMA, astronomers were to study the gas clouds surrounding black holes and explore their properties. That also applies to the black hole in the middle of our own Milky Way. To establish its existence, astronomers invested years of observations and calculations. The first step was to observe the stars in its vicinity as closely as possible. Astronomers discovered that the complicated paths taken by stars as they whiz around a central point can only be explained by assuming the existence of a huge mass, 27,000 light years from our own sun, and 4 million times heavier. A massive, invisible center of gravity, a black hole. ALMA astronomer Kartik Sheath is eager to learn more of its secrets.
The amazing thing about ALMA is that for the first time, we have the resolution to be able to look very, very close to a black hole because of ALMA's superb resolution. And by measuring how the gas is moving around the black hole, we should be able to learn exactly what is feeding this monster in the center of the galaxy. How does the black hole eat? What does it eat for breakfast? How does it grow over time? That's the question we're answering.
Astronomers are currently observing something extraordinary. a gas cloud is getting very close to the center of our Milky Way. After initial observations, astronomers calculated how the gas cloud would be disrupted by the black hole in the next years. One part of the cloud will be able to escape. Another will be sucked in and devoured by the insatiable galactic monster. ALMA needs to penetrate the darkness to discover how this cosmic drama unfolds. The Shanantur Plateau is ideal for radio wave observations. It's large enough for ALMA's huge antenna field, and at over 16,000 feet, so high up that the thin atmosphere offers almost no interference for reception. But while conditions are perfect for the telescope, they're a major challenge for the humans who must live and work here. The road to the ALMA base station leads through the barren land of the Atacama Desert. Here, the Andes Mountains block nearly all precipitation. With less than half an inch of rain per year, the Atacama is one of the driest places on Earth. Each day, 4 large tank trucks transport tap water for around 500 people at the control center and at the antenna maintenance sites. Vital drinking water is delivered in bottles. Everyone at ALMA seems to have a bottle of water nearby. The extreme dryness and the low oxygen levels at this altitude put an enormous strain on people working here. There's a reason why the antennas are assembled here at the base station. Commissioning scientist for the ALMA Observatory, Denis Barkatz, knows the problem well.
Right here, we're at 3,000 meters. I can think more or less coherently. I try to answer questions coherently. That's okay. If we were doing this interview at 5,000 meters up there, the answers would be a lot more interesting. Because your brain, your body, your lungs, everything is not built to function at 5,000 meters. And although people go up there on a daily basis to work, most of the people who have to do work that remain intelligent use oxygen to keep doing that work.
Working at these altitudes can be dangerous. Dizziness, passing out, and even edema of the lungs are always a threat. The lack of oxygen affects both stamina and judgment. A mistake while handling these huge pieces of equipment could prove fatal, which is why everyone who works up here carries a portable oxygen system. And there's plenty to do. The equipment needs regular maintenance and repair. But most of the work involves repositioning the antennas. That requires unique, enormous vehicles which are custom built for the job. Depending on the type of astronomical observation, the antennas are frequently shifted, sometimes closer together, then further apart. Precision is essential, especially when moving telescopes that weigh over 100 tons. Only the perfect interplay of humans and technology can ensure that ALMA's observations are scientifically useful. And only ALMA's accuracy will be able to answer the riddle of the birth and death of galaxies. How do stars grow, expand, and die? What happens to the planets surrounding these distant dying suns? ALMA radio dishes in Chile provide a rare glimpse into the life cycle of distant stars and galaxies. This process of the death of stars is what ESO astronomer Matthias Merker is working on at the Argelander Institute in Bonn, Germany. His research target, from a galactic point of view, is not very far away. A red giant in the Sculptor constellation, only about 1,000 light years away.
The life cycle of stars is basically that stars will form in large molecular clouds where they collapse, and when they become dense enough, they will start burning hydrogen into helium. And this is basically what most stars are doing. This is what our sun is doing right now. It's fusing hydrogen into helium. But once the hydrogen is used up, the star will blow up and become a red giant and start losing mass from its surface. And those are the old dying stars that I'm working with.
His research concentrates on the vast mass of material that the dying star blasts into space.
Red giant stars will lose mass throughout their entire evolution until they die, but at relatively low rates. But every 10,000 years or so, the star will go through a thermal pulse, which means that it will burn helium very rapidly inside the star. And this releases a burst of energy for only a few hundred years, which causes the star to restructure and increase its brightness. And the increase in brightness will also cause it to lose a lot more mass for these few hundred years, and also at a higher velocity, and sweep up material. And because it continuously sweeps up material, it gets formed and pushed into a very thin shell that expands away from the star. And this shell is what we call a detached shell.
Up till now, this shell around the central star was very hard to study. With ALMA, however, researchers can now see inside this gas envelope and create cross-section images of it. And the high resolution has brought surprising detail.
When we proposed for the observations, we thought that it was going to be a star that originally was very similar to our sun, possibly a little bit more massive. But the ALMA results showed us that, in fact, it's a very different system compared to our sun, because it is not only a solitary star sitting alone in space, but it turns out that it has a companion star orbiting around it.
This newly discovered companion star, completely unknown until now, creates the extraordinary pattern reflected in this computer simulation.
The companion is already forming the wind into a spiral, but at 0 years you will see that now the star is going through a thermal pulse, and you can see this very bright detached shell expanding away from the star. And the companion will then shape the wind after the thermal pulse into this very clear spiral structure, which is expanding along with the detached shell.
The unexpected discovery of the spiral structure is only one example of the new findings that ALMA now makes possible.
The ALMA data that we have now was taken during the cycle 0 of ALMA Early Science, and only taken with 16 antennas, and is already incredibly more than we ever expected to get.
ALMA needs 66 antennas to be fully operational. Special vehicles were built to transport the radio telescopes, which weigh more than 100 tons each. There are only 2 of these vehicles in the world. One's called Lori, the other Otto. 65 feet long, 32 feet wide, with 28 separately driven wheels. These monster trucks serve a single purpose: to transport the ALMA antennas. Loaded with an antenna, the 700 horsepower truck reaches a maximum speed of 7.5 miles an hour. The 17-mile stretch of road between the base station and the antenna fields is not without danger. When the transport is underway, all oncoming vehicles have to pull over and wait for safety reasons. After a 5-hour uphill trek, the giant vehicle reaches the 16,000-foot-high plateau with its precious cargo intact. The next step, Offloading the antenna and fitting it into place on the massive concrete foundation takes a gentle touch. Finally, the technicians anchor the antenna and connect it to the supercomputer. Now, the antenna can start to work, helping to solve the mysteries of the cosmos. As ALMA becomes fully functional, it will be able to explore the most profound question in astronomy, the search for life itself. ALMA has revealed the birth and death of planets and even stars. But these processes are of vital significance in the search for the origins of life. Because the chemical elements that we're all made of were created in the core of the stars before being flung out into space by massive explosions. This means that we human beings are also an integral part of the eternal cosmic cycle. Anthony Remajan is an astrochemist with the National Radio Astronomy Observatory in Virginia. His specialty is the search for organic molecules in space.
So we're trying to figure out how actually organic chemistry does happen in space. It's not as simple as going into a chemistry lab here on Earth and taking a bucket of this and a bottle of that, putting it together and forming organic molecules. Space is doing it has been doing it for billions of years, and is forming some of the largest organic molecules that we find here on Earth as well. And we're still trying to figure out how space is actually forming these large molecules.
New technology and testing methods have led to tremendous progress.
ALMA is going to give us the highest resolution. That means we could see the smallest details of regions in the galaxy that are actually doing chemistry. And ALMA is also going to be the most sensitive telescope in the world to detect these large molecules in space.
To be able to recognize molecules such as these, their characteristic radiation must first be established in laboratory experiments. These are then compared with the signals from space, and this is how they're identified. 5,000 miles away from Chile, in a basement lab at the Smithsonian Astrophysical Observatory, Michael McCarthy and his team creates these snapshots of galactic chemicals.
So the molecules have essentially a very specific, unique, what we call a spectral fingerprint. And no two molecules are alike in that sense. The types of molecules we see in space are really quite unusual and exotic by terrestrial standards. So these are molecules that have a very short lifetime on Earth because they rapidly recombine with other species. So we have to, in the laboratory, effectively reproduce the same molecules that are produced astronomically.
Here in the lab, these molecules are created under conditions that mimic the deep void of space.
What we actually do is we mix gases together. So we know exactly what we put into the experiment. We put, for example, methane or water or methanol, for example, into typically in the gas phase, and we dilute it very, very heavily. And the gas expands into the middle of this large empty chamber, and the temperature drops from room temperature, which is 300 Kelvin, to about 1 degree of absolute zero. And we, for just a fraction of a second, pull the plunger back and let this gas rush down a very narrow channel where we apply a voltage between two electrodes. And that voltage, basically, like a light bulb, lights up for a fraction of a second. And all sorts of chemistry occurs. Molecular bonds are broken, and chemistry occurs. Reactions occur, in some cases, very fast.
Within fractions of a second, the lab captures a fingerprint of a molecule as it would look in deep space. And this fingerprint is used by the researchers at ALMA to compare with the data they find on distant solar systems.
Radio astronomers know exactly the fingerprint of these molecules when they look for them by remote observing, in this case with ALMA. And so it gives us great confidence. There's no ambiguity when someone does an astronomical observation. There's no wiggle room allowed. So if the molecule exists in space, you know exactly these frequencies. If it's there in space, we know it. And that's really what ALMA is going to allow us to do.
Already, ALMA has made a startling discovery, one that may change everything we thought we knew about space. Deep in a galaxy light years away, ALMA has detected the building blocks of life itself. "450 light years from Earth, in a cloud of debris around a newly hatched star, the ALMA telescope detected the first complex organic chemicals, the building blocks of life. The groundbreaking discovery was made by astronomer Karin Oberg, and she made it by accident.
We were looking for so-called heavy molecules, molecules that have a deuterium atom instead of a hydrogen atom in them. But what we also saw was emission from complex organic molecules called methyl cyanide, so it belongs to the cyanide family. But turns out to be a very important molecule when you're thinking about the chemistry that led to the origins of life.
Scientists had long suspected that organic chemistry existed in other galaxies. ALMA has finally proven it. The discovery has enormous implications for science.
In an even grander scheme, methyl cyanide molecule and other molecules like it were very important in the chemistry leading to the origins of life on Earth. So it's of course very, very promising that it's common also elsewhere. So it seems to remove one more barrier towards having life being common in the universe.
If organic chemicals are common throughout the universe, it means that Earth may not be so special. And life as we know it may actually be found on distant planets through tools like ALMA.
I mean, it doesn't really matter which culture you come from. Origins of life is a profound question. I mean, it's just one of those questions that I think basically everyone at some point in life asks themselves, like, how did we get here? Are there other like us out there, or at least something similar?
An international effort to build a massive telescope on a remote plateau in Chile has led to the first suggestions of life in distant galaxies.
ALMA is a game changer. It is really a fantastic telescope.
Organic molecules are a distant step from hard evidence of alien life forms. The scientists at ALMA are using this evidence not only to search for extraterrestrial biology, but also to discover the keys to the creation of life on our own planet.
What we're looking for is the building blocks, the fundamental molecules that build up things like RNA, proteins, and amino acids. And so if we could figure out how these molecules form in space, and we could figure out how they get to the early Earth, then we are answering the question is how the building blocks of the organic material that make up you and I, how the material that makes up RNA, self-replicating molecules, actually formed and can evolve on early planets. And we think that that starts in space.
The search for organic molecules in cosmic gas clouds leads to far-reaching questions. Do the building blocks of life really originate in space? And if so, how did they land on Earth?
We also know that this organic material is contained in things like comets and meteorites and asteroids. And during the stages of planet formation, during the stages of star formation, there is a period of what's called heavy bombardment, where we know that planets get constantly hit with comets, meteorites, and asteroids. So the same organic material that is floating out there in space, that gets bottled up onto comets and meteorites, could actually be seeded into these early planets. And so the same material that eventually led to the formation of life on Earth, the same organic material that we know is floating around in space, could be seeded onto planets throughout the galaxy and possibly kickstart the formation of life on those planets as well.
If we consider the increasing number of newly discovered planets orbiting foreign suns and the many organic molecules in space, it seems unlikely that life could only exist here on Earth. And who knows what else ALMA will find in the furthest reaches of space. The search for our cosmic origins has taken us to one of the most alien places on our planet. Almost like an outpost of some as yet uncharted territory, the ALMA Control Center nestles on the slopes of the Andes. With ALMA, astronomers are now beginning to see previously hidden details, and they anticipate that more new and unknown facts will come to light. Their findings will lead to a whole new image of the universe. Because the story of the stars, of planets, and of life itself does indeed lie in the darkness, where only the eyes of ALMA can see.